Good morning. It is January 23rd, 2022. Welcome to the English Sunday School class for Yongsan Baptist Church. It is a little warmer in here than it has been lately. That's why I don't have the jacket on. Appreciate your patience. For those of you that have been following along, we missed a few weeks of videos. That's my fault. I let myself get sick. A little too weak. But appreciate the prayers. It wasn't COVID, no matter who's making accusations out there. And the Lord answered many prayers. Guys back here, we're all better to go. Better and good to go. And we're going to pick up where we left off. We did in our lessons of looking down. We were talking about polonium radio halos and that evidence of God's creation in the flood and in the geological record. So, still in geology for a little while. Radio halos, the three-part article that we're pulling this information out of talks about these vanishing bullets and things like that, just different kind of mechanisms and metaphors to help you remember. Geologists have uncovered a great mystery in granite, specifically in granite rocks. They find tiny black circles known as radio halos. This is probably the clearest photo I could get of a radio halo. They were caused by the radioactive decay of polonium, but the source in the center has disappeared. Where did it come from? Where did it go? And the only answer, as you'll see in this lesson, is a global flood. Once you learn more about these features, you will see why they mystify geologists. They are hard to explain if granite formed slowly over millions of years, but they make perfect sense if molten material rose near the Earth's surface during the worldwide flood and then quickly hardened into granite. But first, we need to understand a bit more about radioactive decay and its effects on rocks. So uranium decay is very well known. Geologists clearly understand the radioactive decay of uranium atoms and the decay's effect on the surrounding rocks. We can observe this process today. It's not a mystery. The nuclei of uranium atoms are so large that they are very unstable, as we talked about a couple of weeks ago. As the atoms decay, subatomic particles, or alpha particles, fly out like bullets, damaging the surrounding material. These bullets produce spherical halos called radiohalos, which is an abbreviation of radioactive halos. After the first set of these particles is ejected, the smaller nucleus is still unstable, so more particles are ejected from the nucleus. This happens repeatedly until the atom becomes stable and no longer decays. In what is known as uranium decay chain, this graphic here, the nucleus of the original uranium-238 atom typically undergoes 8 levels of decay, of alpha particle exchange basically, until it becomes a stable lead-206 atom. So the intermediate steps during the radioactive decay of uranium-238 are shown resulting in the final stable lead-206. When we talked about the dating methods, we talked about uranium-lead dating, right? And strontium, rubidium dating, and these different kinds. And it's what they start from that's radioactive and what they go to that is no longer radioactive. But there's a lot involved in getting there. So where the arrows are down, the red arrows that point down, those changes are alpha decay. They give off alpha particles. All of the ones that point down, even the black ones, are alpha decay, but then specifically the red ones are halo-producing alpha decay. So we have halo-producing alpha decay for most of this, and then these don't produce specific halos separate from them. That's a little confusing, but the arrows pointing upward though, these here and here are beta decay, where we talked about the difference between alpha, beta, and gamma decay. In beta decay, whereas in alpha decay, there's 2 protons, 2 electrons being given off as an alpha particle, which is helium, and that particle is then moving super fast and tearing through the surrounding material that it's in. In beta decay, it's splitting a neutron, and then it loses an electron and gains a proton. So it's a whole lot different process, and really what is being spit out in beta decay is the electron, but it changes the nuclei count because of splitting a neutron and adding a proton. So the original or parent uranium nucleus that we can start with here is 238 because it contains 92 protons. then on the periodic table it would be number 92, right? Uranium is number 92 on the periodic table because it has 92 protons. But it's 238 because it has 142 neutrons. 142 neutrons, no, that's not right. 146. Yeah, we'll get there. 146 neutrons and 92. What's the math? I don't know. I'm bad at math. I just think I typed it wrong. But the total number of neutrons and protons is the isotope number for the radioactive element. So here we have a uranium atom that's number 92 with 92 protons. Once it spits out its alpha decay with the 2 protons, 2 neutrons of a helium atom, it becomes 90, right? But 90 is not the number of uranium. 90 is the number of thorium, the TH here, which is 234. So that atom then becomes thorium, but thorium is also not stable, so it decays radioactively through beta decay, and it splits. The splitting, ejecting 2 electrons or beta particles, gaining 2 protons, giving it 92 again, but bringing it up here, right, to uranium again because it has 92 protons, but it has fewer, instead of 146 neutrons, it now has 142 neutrons, so instead of uranium-238, we're at uranium-234. Is that clear as mud? Basically, we're giving off alpha particles, doing beta decay, we're back at uranium for the next halo. This gave a halo, this next halo is also uranium. We'll have a different chart in a minute that'll kind of explain the circles themselves. But the nucleus of the uranium-234 atom is still unstable, so it continues to decay. Again, back to thorium, but with a different number, so it doesn't beta decay. It continues alpha decay along this line, creating a halo every time. So the picture is more complicated. The process continues until we get to Let's Go 6, but it's more complicated down here at the bottom because of branching, right? So at polonium-218, right here, it starts branching and doing multiple things at once. Polonium-218 atoms decay to lead-214 and then quickly decay to bismuth-214 and then polonium-214. The main decay path is depicted with the solid red arrows, right? So we're following this is the main decay path, but there's other things branching off of it. And the main 8 alpha decaying atoms are shown here in red. So the last one is polonium-210. So this figure, as we talk about the mystery of polonium radiohalos, this is figure 1 in your notes, a little bit larger than the others, and I don't know how clear it is on that piece of paper versus how clear it is here. I had to blow it up a little bit. This figure shows a sample radiohalo that results from the decay process we just described, and you can count the 8 rings associated with it that go all the way out. And again, under an electron microscope, they have a lot clearer ability to work on this. And then we talked about the levels, the layers of the biotite that they carve out. And they try to find perfectly that one right in the middle that has all the layers and still contains the zircon crystal in the middle. Again, we'll get to a diagram that'll make this a little more clear. But why 8 and not just 1 ring? Glad you asked. As each of those alpha particles is fired out from the nucleus, each of them has a different energy. Because it's a larger, more unstable alpha particle decay has more energy to shoot the alpha particles farther away. And then as you get less energy, they go less of a distance. But also, that doesn't necessarily mean that as we go down the decay path, that those have less energy. It all depends on how stable or unstable that atom is. But each bullet travels a different distance, and the ring is where the particle stops and then causes the most damage. That alpha particle is causing damage through this path. It's darker in here because all of the particles go through this part. But where it stops at the ring, that's where, as that alpha particle is stopping, it causes the most damage along its pathway. And then creates that ring, leaves a mark, if you will. The origin of 8-ring radiohalos is not a mystery, like we said. They form from uranium-238 decay. The mystery, though, is in figures 2 through 4 of the 1-ring, 2-ring, and 3-ring radiohalos. So figure 2 is a 3-ring radiohalo. There's one here, one here, one here. Figure 4 is a 2-ring. There's one out here and one right here. And this is only a single ring in figure 3. So the question is, how did these form without the multiple rings? Okay, we can see the source of the 8-ring radiohalo because it's still there. It's a zircon crystal that still hosts uranium that can still be found in the center of that halo. But nothing is usually visible in the center of these radiohalos. Fortunately, it's still possible to determine the source of the rings by carefully measuring the distance between them and looking at this diagram. By carefully measuring the distance from the epicenter to that ring, scientists can identify which element is responsible for that radiohalo. So in each case, the smoking gun of the 1, 2, and 3-ring radiohalos is a variation of the element polonium. Polonium-218, polonium-214, and polonium-210 all generate exactly the right amount of energy to produce the 3-ring, 2-ring, and 1-ring radiohalos. The problem is that polonium is never found alone in rocks. It's a rare, unstable element that appears quickly during the decay of uranium and then decays into stable elements such as lead. The only possible source of polonium is the decay of uranium, but we do not find a uranium source inside the polonium halos. So, but the crucial clue here is that it is polonium's appearance in the decay chain of uranium. So, there's a whole lot of stuff here. We can talk about possibilities. I'm going to skip ahead a little bit to kind of where it makes sense, because there are possible sources that don't make sense especially in the evolutionary worldview. But in our worldview, the source of the uranium radiohalos is still there. And what I mean by that is the zircon crystal that's still in the middle of the uranium radiohalo that still contains uranium is the source for the polonium radiohalo. It can't be that polonium is moved over here. And that's because polonium-218, 214, and 210 have, we talked about half-lives before, right? A half-life of a decaying atom, of any radioactive atom. A half-life is how long it takes for half of what's there to decay. And science has said that, or from just a general perspective, after 7 half-lives, all of it is gone. It's immeasurable after that point. So you have a maximum of 7 half-lives for a radioactive element to continue to be in place, right? But polonium 218 has a half-life of 3.1 minutes, right? We won't talk about 210. 210 has like a 138-day half-life, so there's plenty of time for that. I mean, not in millions and millions of years, but that alone is, by comparison, that's not that short. 3.1 minutes, right? We're talking about less than an hour if you only have 7 half-lives, right? Less than half an hour. That would have to move the polonium. There was some force would have to move the polonium out of that zircon crystal over here so it could then make its own halo. And all of its decay would have to occur, again, in less than that 20-minute window. But it's even worse because polonium-214 has a half-life of 164 microseconds. So polonium-214, in order to make its radiohalo in one of those 1, 2, or 3 ring, the 2 or 3 ring radiohalos, in order for polonium-214 to have done that, it would have had to been moved and decay in less than 1/100th of a second. Okay, so that's unreasonable. We don't know any force that can do that can move it out and still let it record, because the recording of this radiohalo in the granite, that granite has to be forming solidly enough for there to be a solid material for the radioactive decay to work on. Because the radioactive, if the radioactive element is decaying in magma, it just burns up. There's nothing solid for the halo of this biotite, right? The halo can't record. So it has to be solid enough for the radioactive decay to make a mark. but still malleable enough that it's not completely hard, and thus not allowing for the alpha particles to move. So there's this window of still has to be warm, but it has to be partially solid, and it has to move extremely quickly. So the answer here is most likely, from a creationist point of view, that a particle in the radioactive decay chain, we'll go back to this, something in the radioactive decay chain before polonium is what's being moved, right? And so that would probably be radon. Radon-222 could be moved through, put an arrow on it, fancy. So radon, once this decay rate gets to radon-222, this whole biotite sheet will still have massive amounts of hot water, right? Let me see if I can read this off. So under normal conditions like we see in the Earth today, the migration would be impossible. To understand the magnitude of the problem, you need to understand how polonium atoms had to migrate and how quickly they had to travel. We talked about that. The 100 million, scientists have estimated that each of those radio halos takes about 100 million alpha particles. And so it doesn't become dark until about 500 million alpha particles. And then it doesn't become very dark, like we saw in the center, until 1 billion alpha particles have been ejected. So this means that each polonium radio halo needs at least 500 million polonium atoms to be flushed past that point. Many radio halos often appear in the same specimen, so that means many billions of polonium atoms had to move into position to explain the radio halos that we see. The problem with how fast, we talked about the 1/100th of a second. So a possibility here is to move the element radon-222 into place, and then it decays into polonium. But we also don't find any radon in these locations. Somehow, the polonium had to separate from the radon, then concentrate in what will become the polonium radio halo centers, and then different chemical properties of radon and polonium suggest the solution. I think we have time for the solution. When uranium and polonium radio halos are observed under the microscope, their radio centers are actually on the same sheet of the biotite layers, right? As I mentioned earlier, radio halos are found in the dark flecks within granite called biotite, and these biotite flakes consist of layers that can be peeled back and examined under a microscope. Water can easily travel down the spaces between these sheets, all these lines here. Water can easily travel because of how small water atoms are, or the molecules are. Water can travel through there, especially when it's hot. So the changes to the biotite color are often evidence that water has seeped in between the sheets, and we see that all the time in these biotite specimens. In that very opening slide that I had, where it's all discolored and weird looking, all of that is evidence of water seepage. So when granites crystallize and are cooling, the hot water that's left over from that is capable of seeping along these lines, flowing quickly and consistently through the biotite. And as they pass the zircon, the water can then carry away the radon-222 atom that leaked out of the zircon crystals and transport it between these sheets and get stuck somewhere else. Radon atoms are chemically inert. They don't combine with any other atom. But once they decay, the newly formed polonium-218 atom would readily combine with other atoms such as chlorine or sulfur. And that, dissolved in the hot water, would then flow between the biotite sheets. Polonium chlorides and polonium sulfides don't dissolve well in water, so they wouldn't be carried away with the water, they would get stuck. Then they would start forming these polonium radio halos. The water would continually move through the sheet, providing more and more polonium in the same process until enough builds up to create these halos. So it is a way, right? Whether we can say absolutely this is the way it is, don't know. But it does make sense within the worldview of creation. It doesn't make sense within the worldview of evolution. Ever since 1981, when there was a geologist in a court case in Arkansas about teaching creation in public schools, he dismissed this evidence as a very tiny mystery. So scientists, most secular scientists, have laughed it away and not paid any attention to it. But creation scientists have continued to do research in this in different countries, on different continents, with different samples of granite, and are constantly putting more data out into the peer-reviewed scientific world on this subject that is still unanswerable from an evolutionary perspective. The problem is that secular geologists believe these host granites took millions of years to form, but we see now that the process had to be much faster, only hours or weeks at absolute most, for polonium radiohalos to appear. They shouldn't exist at all, according to conventional wisdom. But though they're very tiny, these polonium radiohalos have a huge message that cannot be ignored. Their amazing testimony to the flood found in granites all over the world point to the catastrophic origin of these granite rocks, and it's consistent with the biblical timeline for Earth's history and God's judgment during the flood. Next week, we're going to look at the last lesson about this radiohalos and the profound implications of radiohalos on all of geology. Hope you can stay tuned for that one. All right, let's pray. Almighty God, we thank you for the day you've given. We thank you for the time we have together. We thank